Hi, everybody. I'm Jian Wang from Beijing Jiaotong University. Today I will present defending against the memory inference attacks for iteratively pruned deep neural network. This work is with Jing, Shang, Kailun, Wang, who are my students. Jiqiang from Beijing Jiaotong University, Jiang from Beijing University of Technology, Armanuzzaman and Ziming Zhao from Northeastern University. With the rapid development of the deep neural networks in recent years, the scale of the models has grown significantly. However, it's difficult to apply large-scale model on device with limited resource. In this context, neural network pruning have been a widely used model compression technique. With the main idea of the neural pruning is remove redundant parameters and minimize utility loss. Traditional neural network pruning is one shot, and it includes 3 stages. And first, an original model is trained. Then, a sparse model is obtained by parameter pruning. And finally, pruned model is obtained by fine-tuning in sparse mode. Some recent study has shown iterative pruning can achieve better trade-off between model utility and sparsity. In this paper, we studied member inference attack. In a block MRA, an attacker collects data samples and queries model to obtain its outputs. The attacker can compare prediction confidence with a threshold to determine if the sample was part of training set. This underlying issue is DNA trained to memorize training data. Recent work has further found that fine-tuning operations in one-shot pruning increased model's memorization, making the pruned model more vulnerable to MIA than the original model. This is an interesting research questions. Will an iterative pruned model become even more vulnerable to MIA? To answer these questions, we first investigate relationship between the using data and the increasing memorization. The result shows that reusing training data amplifies the model's memorization. Further, we find the MIA accuracy of the iterative pursued model is higher than that of one-shot pruned model. We further find that inherent easy-to-memory training data are more vulnerable to service privacy. As shown in this figure, attacks will more accurately identify data with high memorization scores as a member sample. In short, we find that the reuse of the training sample and the inherited easy-to-memory characteristic of some sample are the 2 main factors contributing to increased memorization during the iterative pruning. Therefore, we pose the a defense to weaken memorization by addressing these factors across the three scenarios. The first scenario, we consider that impact of data reuse. Use the entire training set in each fine-tuning epoch, increase model's memorization. The second addresses easy to memorize data, where the model retains a stronger memory of certain sample during the fine-tuning. The last scenario combines both factors, reusing entire dataset with return a deeper memory of easy memorized sample, amplifies memorization and privacy. We propose we mine defense work for this. The framework consists two stages. The first stage involves training an original model and generating memorization scores. The second stage, namely memorization weakened pruning. Iterator prunes and fine-tunes the model with weakening its memorization. Our framework employs three memorization weakening primitives. The first is memorization score-based data ranking, which rank data within each class based on the memorization scores. The second is sliding windows-based data sampling. The last primitive is additive regularization, which applies where L2 regulation intensities based on the data privacy risk. By combining these primitives, we propose three memorization weakening methods. The first method, we introduce the ranking-based sliding windows defense, ISW. The second, we propose risky memory regularization defense, IMI. The last, we combine ISM and IMI to address both factors, SWMI. In evolution, we use 6 data sets and 4 neural networks models. For defense setting, we use 3 window widths and 2 sliding step size for each data size, and set the memory score threshold respectively. We first evaluate the impact of our approach on the prediction accuracy of the model. For the ISW and SWMI method, as the window size decrease, model prediction accuracy declined due to the limited training data available for fine-tuning. For MI defense, we found that in most cases, the privacy utility trade-off is better when lambda I is the middle coefficient value we set. As for defense effectiveness of ISA and SMI, in general, small window combined with small step size can achieve better defense effects in most cases. And under the same window setting, the SMI has better defense effects than ISW. We also compare Wang's performance with several existing defense, as shown in the figure. We found that Wang offers a better price utility trade-off. For the time cost, ISW performs better due to its sliding window sampling, which reduces the train data per acre and speeds up the fine-tuning process. In conclusion, we identified date, reuse, and the easy to memorize characteristics of some samples as key factors increasing memorization during the iterative pruning, which heighten privacy risk. We consider these factors separately and combined impact across 3 scenarios that make iterative pruned model more vulnerable to MIA. We propose WMI, a defense framework, the weakening memorization to engage MIA. Thanks for listening.
Talk. Any questions? Cool. I have one regarding the easy to memorize data. So seems like you train a model to decide the score, right? So how do you get the score exactly? Do you just like use the loss of each sample, or how do you get the memorization score?
There's some work has give the score how to compute. In our work, we use the all entire data set, and we select the data set in different block. So we do some observation to fast this calculation. So it not use all the entire data to calculate at the same time.
Okay, and it's also like connected to the model, like the training model being used, or the architecture, because I think in your slides it says something about using the original model or original.
Yes.
So would that? So is there a more generic way? Say like if I don't know, if I don't have prior knowledge to the model architecture, can I use some kind of memorization score pulled out from a different model and use this?
Yes.
Yeah.
This work is on the data on the data side.
Okay.
We do some work on the data, and we test our work in different models.
Great. Thank you so
Okay,
much.
thank you.
All right. If no more questions are going to be asked, this will conclude our session. Thank you, everybody, for being here.